Hi everyone, welcome to our 12th lecture. This lecture is on the conservation of energy applied to the simple harmonic oscillator, and it is only for the non-calculus students only, okay, because proper analysis of this requires calculus, and so if you're a calc student, you need to watch the other video. What I'm going to do in this lecture is I'm going to take the conservation of energy, which is where we left off in the last lecture, and apply to the simple harmonic oscillator, and we'll be able to see some things about the simple harmonic oscillator that we couldn't see by just doing uh, 1D kinematics. Let me just quickly remind you of what we did last lecture. Last lecture I showed you that there's a class of problems where if you apply Newton's laws to them, the details of the intermediate path is actually quite irrelevant and it drops out. And to illustrate that, I used the roller coaster. I said, what's the velocity at the bottom of the roller coaster? And it turned out to really not be dependent on the shape of the track. It just depended on the vertical drop and the initial condition. And so that was very interesting because, that made that problem so much easier. And this turned out to lead to the work energy theorem. It wasn't a proof of the work energy theorem, but it was an illustration of the work energy theorem. And what the work energy theorem says is that if you do total work on an object, then that's going to lead to a change in its kinetic energy. And the work is the total work is made up of the individual works due to each force, and the work due to any one force is just the force multiplied by the displacement multiplied by the cosine of the angle between the force and the displacement, and you just add that all up for all the forces that are acting on an object, and that's going to equal the change in the kinetic energy, and the kinetic energy is calculated as 1/2 mv squared. So the change in the kinetic energy would be that you would calculate the kinetic energy at the end of the motion and subtract that from the kinetic energy at the beginning of the motion, and that's your change in kinetic energy, and that's got to equal the amount of work that was done by the forces on that object. Now that isn't exactly conservation of energy. The work energy theorem applies to every situation, but for the problems that we're going to do this semester, we had to bracket out friction, okay? Because friction converts energy into yet another type of energy, which is called heat, which we'll study next semester, okay? So I'll say a little bit about what friction does to conservation of energy in the next lecture, but a full understanding of friction and these non-conservative forces and energy, that'll have to wait till we study heat next semester. So what we did was we took the total work done and we broke it up into two pieces. One piece was the work due to conservative forces, and the other piece was the work due to non-conservative forces. And there's only one non-conservative force that you need to worry about, and that is friction. So these non-conservative forces, because they messed up conservation of energy, we just said, you know what, let's bracket that out and let's just consider problems where there are no non-conservative forces, okay? In other words, problems where there's no friction. And in that case, we could take the work due to the conservative forces and we could write that as a change in this quantity called potential energy, okay? And what potential energy is, it's the energy which is in an object because of its configuration, okay? So the two potential energies that we looked at were the potential energy due to height, or due to gravity, and the potential energy due to a spring. So, if you have a block and it's at a certain height, it has a certain potential energy mgh, and if you change it to a different height, then it'll have a different potential energy mgh. And I think you can easily picture that the higher the block is from the ground, the more damage it would do when it hits the ground. And so, as mgh, as the h in mgh increases, you get more and more potential energy. When the block is just sitting there at a certain height, you're not seeing that energy. It's stored in the block, and that's why we call it a potential energy. It's energy which is potentially there and can be released. It's released if I release the block, and then that mgh will become energy as the block falls, and it does damage when it hits the ground, okay? The other potential energy we looked at was spring potential energy. If you have a spring and it has a certain length, if you don't compress it and don't stretch it, it just has it has no energy, okay? It just sits there at equilibrium. But if you take that spring and you compress it, the more you compress it, the more energy you're going to put into it, because if you let go, it'll release that potential energy and it'll boink, spring back and give you back that energy. So you could store energy in a spring in the form of spring potential energy, and the formula for that was 1/2 kx squared. I didn't prove that, I just asserted it. It's 1/2 kx squared, okay? And what we discovered was, again, if you have no non-conservative forces, in other words, you have no friction, that if you take the work energy theorem, with the potential energy on one side and the kinetic energy on the other side, you rearranged it, you found that energy was conserved, which means that if you calculated the total energy before, that would equal the total energy everywhere along the path and including at the end point. The energy is basically conserved all the way along the path. And the total energy is made up of two pieces. There's the kinetic energy and the potential energy. So the total energy, combine the kinetic and all the potential energies together, you get this total energy. That total energy doesn't change over time as the system evolves over time dynamically because energy is conserved. As soon as you put friction in there, well, then all bets are off. Okay, so that led us to this conservation of energy. And what I'm going to do in this lecture is I'm going to apply this conservation of energy to the simple harmonic oscillator, and we'll see that we can solve some problems that way. Okay, so let's do a tiny bit of dynamics behind the simple harmonic oscillator to show you where the energy equation comes from. This part I can't fully flush out all the details because it simply requires calculus, but that's okay. You know, for you guys, it's good enough because it'll give you some intuition. Okay, so when we did the simple harmonic oscillator the first time, we just did its kinematics. I just said to you, you know what, there are a lot of things which just oscillate back and forth. Okay, you know, you can you could just flick something like, I don't know, like a piece of glass, and a glass is pretty rigid, but you know, you hit it like a drinking glass, you tap it and you'll hear that it rings. Okay, and if you could look at it under a microscope, you would see that the glass is actually vibrating back and forth. So there's like just lots of things. The little hairs inside your ear, they're not hairs, they're cilia, which vibrate at the different frequencies of sound. That's how you can hear and so on. So, you know, like the number of things that vibrate is innumerable. Um, well, we're going to abstract that and we're going to look at one particular simplified example of oscillation. And you're actually going to do this in the lab where you have a spring here. So this, where my mouse is here, I've got a spring, and it's got a spring constant K. And if you remember from last lecture, the spring constant K is how stiff the spring is, okay? It's measured in newtons per meter, and basically, you know, how many newtons does it take to compress the spring 1 meter, or conversely, how many newtons does it take to stretch the spring 1 meter, okay? And that spring is attached to a mass m like that, okay? And the spring would normally want to keep the mass at equilibrium, which is our x equals 0 there. But what I'm going to do is in this diagram is I take the mass and I compress the spring, and as I compress the spring wants to push the mass back to equilibrium. And so you can see here a force to the right. That force wants to restore the mass to equilibrium. The displacement, which way did I squeeze or compress the spring? Well, that's x, and I compressed it into the negative x direction like that, okay? So the force here is actually called a restoring force because it wants to restore the mass to equilibrium, okay? In this particular diagram, I compressed the spring, but if I stretched it, well, then I would be displacing it in the opposite direction, not to the left, but to the right. I'd be displacing it to the right, x would be to the right. But now the force would want to pull it back to equilibrium, the force would want to pull it to the left. And you'll notice that the displacement and the force are always opposite one another, hence the name restoring force, because it always wants to restore it to the center. The law is called Hooke's law, and it just basically says that the force is linearly proportional to the displacement x, like that. It's in the opposite direction, so there's a negative sign, and then there's a constant of proportionality, like how much force do you get per unit length of displacement, and that's your spin constant K here, like that. Okay, there's Hooke's law. And actually you will do Hooke's law in the lab, and you'll do it very much the way this diagram looks. You'll have a spring attached to a mass, and you'll be on top of a linear air track to remove all friction, and you know the air track will have, you know, a ruler along the side, and so you could say, you know, this is x is equal to 0 is where the spring isn't stretched at all, and then you'll add a little bit of force and you'll stretch it, and then you'll double the force and it'll stretch twice as far. So if you have so much stress, you have so much force, twice as much stretch, twice as much force, 3 times as much stretch, 3 times as much force. F and X are proportional to one another, and that'll come out. It's a very simple linear relationship, and you'll actually be able to measure K for the spring constant, for the spring. Now, it's not obvious that this particular structure for the force, in other words, a force that follows Hooke's law, is going to give you a simple harmonic oscillation. It kind of makes sense because, when the object's out here, it gets pulled towards the middle, or where the object is to the right, it gets pulled towards the left, and so on. And so you're always being pulled towards the middle. And so you could say, yeah, as I move to the one side, I get pulled back this way. And if I move to the other side, I get pulled back that way. And that actually is how the simple harmonic oscillation comes out. What I can't show you is how you can actually use this in conjunction with Newton's second law and show that you get the sine and cosine out, because that requires calculus. But that's okay. If you just take what I said as given, then and use your intuition, you realize that if you have Newton's second law here like this, okay, so it doesn't look like Newton's second law because Newton's second law says F net equals ma, and I kind of reversed it. I wish I hadn't, but I have here. So here's the ma part, and here's the F net. The F net is the restoring force, and you go, well, aren't there other forces there? Yeah, there are other forces. There's gravity down. If I did the free body diagram for this, there'd be gravity down, and then there'd be a normal force up, but gravity down and the normal force up, the vertical forces, they'll cancel because this thing is not oscillating up and down, okay? And horizontally, there's only one force, which is the restoring force. So the net force in this case is the restoring force. And so on this side you have F net, and on this side you have mass times acceleration. That is Newton's second law. You can then isolate the acceleration. You can see that the acceleration is linearly proportional to x, and that means that the bigger x is, the bigger the acceleration is, but in the opposite direction, which is another way of saying that it's always being turned back to this middle. And the only thing that keeps turning it back to the middle is something which oscillates back and forth like that, okay? And when you do this math, okay, with all the calculus, like totally do the math, you're going to have this ratio k over m here. What you wind up getting is, if you write k over m as omega squared, you get that omega is the square root of k over m. This turns out to be exactly the angular frequency that we talked about when we did 1D kinematics for a simple harmonic oscillator, okay? So just to remind you what the angular frequency was, there's a linear frequency, which is how many times something goes back and forth, okay, and that's what you actually measure in the lab. So something that like in 1 second would vibrate back and forth 10 times would have a linear frequency of 10 hertz, or 10 cycles per second, okay? And there's the period, which says how long does it take one cycle, okay, and you could also measure that in the lab. And in my example that I just did, if it oscillates back and forth 10 times in 1 second, then one cycle only takes 1/10 of a second, okay? So the period and the linear frequency are reciprocally related, but the angular frequency has an extra 2 pi in it. And at this point you go, well, why did you do that? Why did you put this extra 2 pi in there? And again, that comes out of the math, because you've got cosines and sines in there, and sines and cosines have a periodicity of 2 pi, okay? So mathematically, it's always omega, but in the lab, it's F. And the difference between F and omega, you'll see the formulas in a minute, is that omega is basically 2 pi times F. So there's an extra factor of 2 pi for omega, okay? So let's not worry about that detail right now. Let's just remember that this is the angular frequency, which has that extra 2 pi in it. And the angular frequency can be related to how stiff the spring is and how big the mass is, okay? And so the actual formula is that the angular frequency is the square root of k over m. This is new, okay? This is not something that we had, that I gave you when I did the 1D kinematics of simple harmonic motion before, okay? So this is new. This is basically the dynamics. It comes out of the dynamics, which again, I can't quite do for you, okay? So there it is. But this formula is kind of intuitive. The square root part of it isn't, but the k over m part of it is. See, the stiffer the spring is, imagine a spring which is really stiff, the stiffer the spring is, the faster it vibrates back and forth. A weak spring will vibrate slowly, and a stiff spring will vibrate fast, okay? And the bigger the mass is, the slower the oscillator will oscillate back and forth, okay? So there's this kind of fun party trick that illustrates this very easily. You get yourself a drinking glass. Say you're like at a wedding or some party, and you have this drinking glass here, and you pour some wine in it, or water, any fluid will do. And what you do is you dip your finger in the fluid, and then you rub it along the top, the rim of the glass. And if you've ever done this, there are YouTube videos that show this. The glass will ring. It makes a sound like that, okay? And then what you do is you pour some more fluid in there, Okay, and what happens is the frequency actually drops. It rings at a lower frequency, and you go, why is it ringing at a lower frequency? The more fluid I pour in, the lower the frequency is. Okay, and I've actually seen a xylophone made with this, where, like, you had these identical glasses with different amounts of water in each one of them, and each one made a note, and the person would actually, able to play like Twinkle Twinkle Little Star by just rubbing back and forth the right glass. It's kind of fun, a little party trick. And here's why: the more water is in, or fluid is in the glass, the bigger M is. The bigger M is, the smaller omega is, the smaller the frequency. Okay, and so there's just an intuitive little, simple little example that you could do at home. Okay, so that's one new little piece of information, but really we're heading towards the energy. Okay, and I need to remind you before I give you the equations for the energy, because we are doing this all intuitively, we're not falling back on any mathematics. I need to remind you about one cycle in a simple harmonic oscillator. So you've seen this diagram before, but here it is again. And basically, since the harmonic oscillator really oscillates along a line, I can't really draw a loop like that. If I flattened it all out, it would just look like a straight line. That doesn't help very much. So I stretched it out in the y-axis a little bit, but it isn't actually looping in the y direction. It's just going back and forth in x. Okay, so it starts here at maximum amplitude to the right-hand side here, like that, and that's x equals a. Okay, and remember what a is. A is the amplitude. It's like the furthest that you've stretched the oscillator from equilibrium. So equilibrium is here, x equals 0, and here you are, you've stretched the oscillator all the way out to x is equal to a. You let go of it, and what's it going to do? It's going to start restoring back to equilibrium, but when it gets to equilibrium, it doesn't stop, it keeps going, and then it goes all the way to the other side to x is equal to minus a, which is the amplitude on the other side. And then it keeps going, and then goes to plus a and minus a, and so on, and it oscillates back and forth, back and forth, back and forth, like that. Okay, now when you're at maximum displacement, when you're at the amplitude, x is equal to a, at that point the oscillator stops, turns around, and comes back. So the velocity is 0 there. Okay, so at maximum displacement, x is equal to a, velocity is 0. Conversely, on the other side, x is equal to minus a, that's the maximum displacement to the negative side, the velocity is still 0, because again, it stops and turns around. At equilibrium, which is right in the middle here, x is equal to 0, but that's where the velocity is fastest. Velocity is 0 at the endpoints, and it's fastest right in the middle. Okay, now we did say that before when we studied simple harmonic oscillation the first time, but now let's think about it in terms of energy. Okay, so the potential energy here is given by 1/2 kx squared. Okay, so 1/2 k, the spring constant, x squared. You'll see the formula in a second. And so the bigger x is, the more potential energy there is. Okay, the biggest the potential energy is at x is equal to a, because it's not going to go any further to the right. That's the biggest x you'll get, is x is equal to a. And so at this point, you've got a lot of potential energy, and the velocity is 0. And remember how you calculate the kinetic energy, it's 1/2 mv squared. If v is 0, v squared is 0, the kinetic energy is 0. So at the end point x equals a here, the energy is all potential. It's all actually spring potential energy, as I stated here. It's all spring potential energy, and there is no kinetic energy at all. Okay, so there's no kinetic energy at the end point. It's the same thing on the other side, on the negative side. Over here, the energy is all spring potential energy. There is no kinetic energy. In the middle, and I indicated that with point A. In the middle here, which is at equilibrium, this is my point B, okay, there is no potential energy because x is equal to 0. So 1/2 kx squared is equal to 0. So there's no spring potential energy, which makes sense because if you have a spring and you don't stretch it, and you don't compress it, you didn't put any energy in it. You didn't store any energy there. Now, I understand that the x is equal to 0 is only going to happen in an instant in time because, before you get to x equals 0, it's stretched and it's got a little bit of potential energy, and then it passes through 0. On the other side, it's going to have potential energy, and only right at x equals 0 is it not going to have potential energy, which is just this very brief instant in time. But at that instant, there is no potential energy. So all the energy must be kinetic. And in fact, that makes sense because that's when you get your maximum velocity. Okay, so when you have maximum velocity, 1/2 mv squared, where v is v max, all your energy is there, and there is no potential energy. So as the oscillator oscillates back and forth, Another way to think about the dynamics is that the energy sloshes between being all potential, all kinetic, and then all potential, back and forth like that. So let's trace this out and think about where the energy is all potential and all kinetic. At the end point here, the energy is all potential. As it starts to approach equilibrium, the potential energy decreases, the kinetic energy increases, and in the middle here, it's like some kinetic, some potential. By the time it gets to point B, all the energy is kinetic, there is no potential. Okay? And then by the time you get to this further endpoint here, we're back to all potential, no kinetic. And so you're going all potential here, all kinetic here, all potential there, all kinetic there, all potential. You keep sloshing back and forth. At an intermediate point, like my point C here, you can't say that it's all potential and you can't say that it's all kinetic. It's a little bit of both. It's a little bit of both, okay? And so intermediate points, you have a combination of the two. All right. Now, let's look at the formulas and see if we can understand them. Again, I really can't derive these for you in the absence of more heavy-duty math, but that's okay because we can certainly understand them intuitively. Conservation of energy says, I don't care where in this cycle, you measure the energy. At point A, at point B, at point C. If you tell me the total energy, and for total energy we're using the symbol capital E, if you tell me the total energy, because there's no friction, there's no non-conservative forces, the energy is the same all the way through that cycle. So I don't know, at point A you find that the energy is 100 joules, then at point B it's 100 joules, at point C it's 100 joules, at every point in that cycle it's 100 joules and it never changes because it's a conserved quantity. Okay, so you can calculate the energy at point A, at one of the endpoints. There it's all potential energy. The potential energy is calculated by 1/2 kx squared, but x is equal to A, and so if the energy calculated at the endpoint is 1/2 Ka squared right there. Okay? That's got to equal the energy calculated at the middle, where it's all kinetic energy, and there the energy is 1/2 mv max squared. Okay, and there's no potential, so no other plus. Okay, and then finally at some point C, which is where it's neither all kinetic and all potential, you can't reduce it to one or the other. You have to have both. Okay, so here this last form here is basically at point C, where you have 1/2 mv squared plus 1/2 kx squared. So you have a little bit of both kinetic and potential energy. All right, so this equation is actually pretty powerful. All right, and it does cause confusion, even though like you might have it memorized or whatever. It causes confusion because you might want to calculate V max, but you say, well, if I'm going to calculate V max, let me just calculate the energy and everything at point B, and you don't have enough information to get the energy at point B. So what you need to do, and we saw this even in problems that we did last time, is that even though you want to look at the quantity, you want to look at some properties at point B, you actually have to calculate the energy at point A because that's where you know all the information. Okay, and so in these problems, it doesn't matter where you calculate that energy. Even if you're focused at one particular point in the cycle, look along the entire cycle and say, can I calculate the energy anywhere along here? If the answer is yes, calculate the energy there and then apply it to where you're looking at of interest. And having taught this course for many years, this seems to be the thing that students get caught up on. It's purely conceptual. It's not really a question of the equation. It's just that somehow you just don't think to calculate the energy over here because your attention is focused over here on solving for something at that point in the cycle. Just keep that in mind, okay? And so there we go. There's the energy, and there are 3 ways to calculate that energy. All right, 3 ways to calculate. Oops, let me scroll down a little bit more. Okay, 3 ways to calculate that energy, like that, depending on what you know. And there's also the angular frequency. This is a new equation. We had the angular frequency before, but now you know that you can obtain the angular frequency from the spring constant and the mass. Okay, and finally, this is what I was alluding to before, the angular frequency is related to the period, which is the time for one cycle, and the frequency, which is the number of cycles you make per second, by these formulas here. And just notice that there's that extra 2 pi in there. So omega is bigger by a factor of 2 pi, again, because behind all of this is the mathematics of sine and cosines. All right, there's all the theory, and so now we can just jump in and apply it to a problem. Okay, so here we have a spring, and the spring has a spring constant of K is equal to 100 newtons per meter, which means that in order to squeeze the spring by 1 meter, you'd have to apply 100 newtons of force, okay? And we attach to that spring a 1 kilogram mass. All right, then we start the system oscillating. Okay, so it's basically the picture that I started the lecture with, but now I've given you some numbers. Okay, K is equal to 100 newtons per meter, and M is equal to 1 kilogram. Okay, the first question I ask is, what's the period of the motion? And you go, well, wait a sec, how do I get that? You didn't give me enough information. There's no frequency in there. I know, but don't forget, it's actually these two equations right here. Don't forget that now we know that the frequency, the angular frequency, is related to how stiff the spring is, K, and the mass attached, M. Okay, and so once you get omega, then you can get the period using this other formula. All right, so let's do that. We start off with omega is equal to the square root of K over M. For K, substitute in 100 newtons per meter. For M, substitute in 1 meter. So we get 100 divided by 1, and take the square root of that, that's 10, and you get 10 hertz, okay, for your angular frequency. Now, to get the period, it's basically 2 pi over omega. T is equal to 2 pi omega. You might say, I didn't see that formula up there. Yeah, I know. If you take this formula right here, and you multiply both sides by omega, and you divide both sides by, divide both sides by omega, multiply both sides by t, this equation here simply becomes this equation right here, okay? So now substitute in for omega, which is 10, and you'll find that the period is 0.628 seconds. Okay, so this thing makes a complete oscillation in 0.628 seconds, a little over half a second. Okay, so there you go. That answers the question. Let me show you the units. I purposely put the units in here to show you that, yeah, these units will turn out to be seconds, and 1 over seconds is a hertz. And it's not obvious, is it? Because, you know, in one place you have like a spring constant, and the other place you have a mass, and you go, well, how does time come out of that? So let me just remind you, first let's start off with a Newton. Remember that a Newton is a kilogram meter per second squared, and that's Newton's second law, just at the unit level, because you've got F is equal to MA. F is Newton, M is kilogram, and A is meters per second squared. Okay, so a Newton is a kilogram meter per second squared, but that the units of K are not newtons. The units of K are newtons per meter. So if you take a Newton and you divide it by a meter, the meter cancels out here, and you just get a kilogram per second squared. So the units of K are kilogram per second squared. Okay, but that isn't all the units, because, you know, I have a Newton per meter here, but I've divided a kilogram there. So if I divide Newton meter and you divide out a kilogram, all you get is 1 over second squared, and that 1 over second squared is under a square root. So if you take the square root, you just get 1 over second. So you get that omega has the units of per second, and that's exactly what we expected, okay, for a frequency. We expect a frequency to have units of per second. Per second is perfectly fine, but quite often we use hertz. Okay, so great. There's the answer to the first question. Let's take a look at my second question here. So I say we give the mass an initial push so that it has an initial velocity of 2 meters per second. Find the total energy and find the amplitude of the motion. Now the question, you know, we're doing it together, so that's okay. On a test, I'd be very precise here. Slightly ambiguous, you might say, well, where did we start? Like, how far from equilibrium? Let's assume that I give it a push of 2 meters per second at equilibrium. Okay, so maybe a better way that I could have worded this would have been something like, we give the mass a push such that it has a velocity of 2 meters per second at equilibrium. Okay, and that would be very clear. All right. Now, why am I obsessing about the wording there? And that's because I didn't really tell you, I indirectly told you Vmax. I didn't directly tell you Vmax. Since the velocity is 2 meters per second at equilibrium, you should know to say 2 meters per second at equilibrium, that means Vmax. Because Vmax is obtained where? At equilibrium. So if you've got 2 meters per second at equilibrium, I indirectly told you what Vmax is. So Vmax is 2 meters per second. Okay? And then you look at these equations up here and you go, what do I know? Oh, I gave you Vmax. All right, and you have the mass, 1 kilogram, and so this particular form here looks very promising. Okay, so we substitute in E is equal to 1/2 mv max squared. We substitute in for mass, we substitute in 1 And for Vmax, we substitute in 2, and that works out to be 2 joules. Okay, so there's the energy. It's 2 joules. It's 2 joules not just at equilibrium, but it's 2 joules everywhere along the cycle. Okay, but that's not exactly, well, yeah, I did ask you for the total energy, but I also asked you for the amplitude. Okay, so what's the amplitude of the motion? So we want to find capital A. There's a couple of ways to do that right now. We can either use the old formula from when we did the kinematics, and that's Vmax is equal to omega A. But since we're doing energy, let's use this other form here. E is equal to 1/2 Ka squared. So once again, just don't forget, there's 3 ways of expressing the energy. There's one way, okay, there's another, and there's another, okay. Each one is the energy at different points in the cycle, but they must all be equal because they're conserved. And so this first way of expressing it looks promising to find A. All right, so over here, we're going to set E is equal to 1/2 Ka squared. E we know is 2 joules because it's 2 joules everywhere. Okay, here we calculated at equilibrium, but here that formula applies to the endpoints, but that's okay because energy is conserved, so it's the same E. 1/2 K is 100 newtons per meter. Okay, so there's the 100 there, A squared, and then it's just a matter of some simple algebra, and you find that A is going to equal 20 centimeters, 0.2 meters or 20 centimeters. Okay, so that answers that question. All right, and then finally, I asked the question, how fast is the mass moving when it passes x is equal to 10 centimeters? Okay, so how fast is it moving? What am I asking for? The velocity. So what is v when x is equal to 10 centimeters or 0.1 meter? Okay, well, I redrew the diagram here to try to show you what's going on. This thing oscillates with an amplitude of 20 centimeters. So the endpoint is actually 20 centimeters from equilibrium. Here's x equals 0, equilibrium right there. That's where the velocity of 2 meters per second occurs. Okay, I could have even written here Vmax instead of V, but it is the velocity at x equals 0. Okay, here we are at maximum displacement. That's where A is 20 centimeters. That's where V is 0. But now I'm saying focus on a point which is 10 centimeters. It's not at equilibrium. It's not at maximum displacement. It's in the middle. It's in the middle. Okay, so x is equal to 10 centimeters. What's the velocity there? And you go, well, how would I calculate that? All right, and that's where that third form comes in. Because if you take a look here, the third form has both velocity and x in it. If you know the total energy and you know v, then you can find x. Or if you know x, then you can find v using that form. Okay, so because we're at an intermediate point, neither equilibrium nor maximum displacement, we're going to use the form E is equal to 1/2 mv squared plus 1/2 kx squared. Okay, E we know is 2 because it's 2 everywhere. All right, 1/2 m we'll put in 1 kilogram, and v we don't know. That's what we're solving for, so just leave the symbol alone. Okay, plus 1/2 k, you put in 100. I gave you K is 100 newtons per meter. And X I told you was 10 centimeters, but in MKS, 0.1 meters. So over here, 0.1 meters. And you'll notice that once I've substituted in all the numbers, the only unknown is V. The only unknown is V. So you have that 2 is equal to 1/2 V squared plus a half, just simplifying the numbers. 4 is equal to V squared plus 1. In other words, V squared is 3. Or V is the square root of 3, and that's 1.73 meters per second. Okay? And that's the answer. Does it make sense? Does it make sense? You should always ask that question. Okay? So let's look at this diagram again. What's the maximum velocity? 2. All right? At equilibrium, it's 2. At maximum displacement, the velocity is 0. So the velocity at some intermediate point has to be bigger than 0 but smaller than 2. And what did we get? We got 1.73 meters per second. You might have incorrectly guessed something like this. You say, oh, it's 2 here, it's 0 there, we're halfway, and halfway between 0 and 2 is 1. So the velocity there is 1, but it isn't. It's actually 1.73 meters per second. You go, well, why did that happen? Because the relationship is not linear. So if you go back to this equation, you'll see that it's not v and x in there, but it's v squared and x squared. And as a result, it doesn't quite work out that way. By the time you're halfway back, you're actually traveling pretty fast, okay? So, you're 0 here, you're 2 there, you're not 1.5 there, sorry, you're not 1 there, you're 1.73 there. Okay, so you're significantly higher than the halfway point for the velocity. All right, and again, that's because everything is coming in as a square. All right. Okay, so that's it for these problems, and there's not nothing really very deep about them. But again, the only thing I really want to emphasize is I've noticed this error being made a lot. Again, I'll ask for the, like in this last question, I asked for the velocity at x equals 10 centimeters. And you'll say, well, I need the energy at 10 centimeters and I can't find it. No, it's the energy is the same everywhere. So look anywhere in the cycle and say, oh, I can find the energy there. Therefore, I can use the energy here. Okay, so there it is. All right, thank you for listening.